Hello, everyone. My name is Hohen Anthony Fernando, and I will be presenting on neural branch prediction for CPUs. So to go over the agenda really quickly, we're going to dive into the background of the topic, talking about branching, processor pipelining, and then finally branch prediction. Then we're going to talk about the early methods of branch prediction. And after that, go into the current research on deep neural network branching prediction methods. And then a final conclusion after that. So to start off with the background, I want to talk about why I chose the topic. I first heard about branch prediction and this topic during an operating systems lecture that I was in, and our professor just offhandedly mentioned how CPUs nowadays are trying to basically predict what the next instruction is going to be. And I found that idea very interesting. And when I researched it, it was a really cool blend of like hardware / lower level topics and a blend of higher level concepts as well. So I found it really interesting. So in order to talk about it, let's recap what branch instructions are. So branch instructions, as you can see in this diagram on the right side, this gives a really good explanation of branch instructions. On the left here, you can see some high level code, and it's just a simple if-else statement. And on the right is the translation into assembly language. And you can see it that it has this BEQ instruction. That's a branch if equal instruction. And so that's the example of a branch instruction. And it does the same thing as this if statement. So it's saying if these two values are equal, go to this true block of code. So then it comes down here and then starts executing at the true. Otherwise, if this does not equate to true, then it's going to just continue on. It's not going to do the branch. It's just going to go to the subtract, which represents the else statement. So next, I'm going to give background on processor pipelining and what that is. So in this diagram here really illustrates the processor pipeline, and it's made up of four stages. First, you have fetch instruction. That's so after your code has been compiled and then assembled and then loaded, the machine code gets fetched by the CPU from RAM. Then it gets decoded and then executed by the CPU in the third stage. And then finally in the fourth stage, it does a write back into the desired location. Basically, the processor pipelining allows for a lot of parallelism for execution of instructions by the CPU, and that's really helpful. Essentially, once an instruction has been fetched, then once that is done, in the very next clock cycle, as you can see, like the next instruction can already begin to be fetched, and that's where you get that parallelism. You're getting to fetch another instruction while the next instruction is getting decoded, and etc. So what is the problem here? So what's the problem with what's going on here? As you can see, we talked about pipelining is really critical to the CPU's performance. It's really important for that parallelism to exist in order for the CPU to really take full advantage of its processing power. And what happens is when you have a branch instruction, it actually blocks the pipeline. You can see that in this diagram right here. This diagram is showing how if you had a branch instruction, what happens is at the execute stage of the instruction, that's when it's going to block. And basically, your pipeline is going to have to wait for that branch to compute to know what the next instruction is going to be. It's not going to be able to fetch the next instruction. So because that it needs to compute the branch, it doesn't know what the next instruction will be, and that breaks the parallelism and it blocks your pipeline, which is detrimental to the CPU's performance. So to solve this, we ask ourselves, can we predict the outcome of the branching condition? And the answer is yes, and that's where branch predictions come in. Branch predictions improve CPU performance by a lot, and they're done via the hardware because it has to be very, very quick. And this technique has been around for a long time. I had never heard of branch predictions before I started researching for this presentation. So I didn't know that it's been around, like this has been a technique that's been used since the 1980s. The early methods that were used started with static predictions, then dynamic, and then perceptron. And we'll talk about these later on. And when we think about like a prediction kind of problem, what we usually think of as computer science students is what we think, can we use machine learning to solve this problem, right? And the answer to that is yes. And that's what the current research is being developed on. But before we talk about that, let's go over the earlier methods of branch prediction. So we started off by using static branch predictions, and this happens at compile time. And the way it works is the branch predictor will basically decide that a branch is either never taken or is always taken. And that is the easiest way, and it's actually very fast because it happens at compile time for branch prediction to be done, but it's not the most accurate. And that's where we get to dynamic, which happens at runtime. So it could be a little bit slower if you're not careful. And it uses a history table, which is usually a table of bits. And it uses that as kind of a flag for whether or not to take a branch or not based on the current history. And then perceptron is really cool because perceptron is a simple neural network, and it's what's currently used a lot in the industry today for branch predictions by CPU manufacturers. It's a single layer, simple neural network finding the correlation between the branch's history and its branch outcome. And it's very useful because it can take in a longer amount of history than a normal dynamic branch prediction. And it's been developed so that it can be implemented in the hardware because that's a necessary part in order for it to be useful in commercial use. Now going on to current research done by a group of Mao et al. And they're doing some research on convolutional neural network branch predictions. And what they did is they basically treated the problem as a binary classification problem, kind of the simplest machine learning task there is. Basically, they kind of categorize it as, is the branch taken or not taken? And they found that convolutional neural networks, or CNNs, they work really well because of their locally connected nature. They found that because convolutional neural networks are more sparsely connected and only connected in the local layers, this supports the highly correlated local data because the local branch history has been, they found was more highly correlated to the branch's outcome. So it really helped them to get better results. And here's an image of what a convolutional neural network looks like. And this is similar to what they use. They use several different versions of convolutional neural networks, but this is a basic representation. Has the convolution layers, the pooling layers, and then these fully connected layers at the very end for the binary classification output. And so the results for their research show that the convolutional neural networks, these bottom four, but specifically these bottom three, the purple, green, and light blue, were really, really high performing at branch predictions. This axis on the left is for misprediction rate, and you can see that their misprediction rate was really, really low as compared to, like, say, perceptrons or even this other deep neural network, the orange one. And that goes to show that the convolutional neural networks worked, like they found, were the most accurate. They found this due to the number of convolutional layers in the network. Like these bottom three had the most number of layers. ResNet 50, the light blue one, has 50 convolutional layers, I believe. So it performed like the best on almost every occasion they found. So in conclusion, branch prediction will continue to evolve as new technologies come about, as machine learning improves, as the hardware gets faster, and we'll likely see industries start to try to adopt more neural network branch predictors. However, there's going to have to be a high focus on the speed performance of the branch predictions, because right now the convolutional neural network has been shown to be really accurate, but it's not fast enough at the moment, and that's the limiting factor. They're going to need to find a way to increase its performance in terms of speed in order for it to be commercially viable. And with that, I'd like to say thank you for listening to my presentation, and these are my sources. Thank you very much.